Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of orbiting bodies and the concept of orbital mechanics. And we're getting to the point where we're starting to pull things together to be able to understand what it means for a body to orbit around another body. In the previous videos, we've laid some of the groundwork that's necessary to complete this topic, and a couple of key things to remember before we get into this video is to remember that orbiting bodies are really related to the concept of moving bodies, since obviously an orbiting body is a moving body. And in a previous video, we talked about Newton's laws, Newton's 3 laws, that will describe how bodies move and some of the details that go with that. In this video, what we're going to do is add to it one final concept related to Newton's laws, and of course, that's Newton's law of universal gravitation. So let's go ahead and get started with that. Now, the first thing that I want to start with is the title, because there's some important parts to this that are just sort of loaded right into the word universal. So prior to Isaac Newton, there was a misunderstanding about what gravity means. There are some misconceptions that people often have. For instance, Isaac Newton does not discover gravity. Gravity is a concept that had been at least understood in a rudimentary way before Newton comes along. Nor does he obviously invent the concept of gravity. So gravity, this idea that things are pulled to the surface of the Earth, is something that has been known for a very long time. But what had not been known before Isaac Newton was all of the details that go with this. And there was this belief that all of the rules that govern life here on Earth were laws that were for here on Earth. Newton comes along and says, no, these rules, these 3 laws of motion and this concept of gravity is a universal law, meaning that it works everywhere in the universe. What he mentioned was the same mechanical movement and rules that govern an apple falling from a tree are the rules that govern how the moon orbits around the Earth or how the Earth orbits around the sun. So he breaks that barrier between rules that are earthly rules and this concept of laws of nature that extend everywhere in the universe. So that's why this is called the universal law of gravitation. It's a concept that works everywhere here on Earth, as well as part of the universe, parts of the universe, obviously, where gravity is appropriate because the Earth is part of the universe. Now, the formula here on the left, it looks a little bit more complicated than some of the ones we'd seen before, but it is actually fairly simple once we dissect it and look at the parts. And let's look at the bits and pieces. The F stands for the force of gravity, and gravity is an attractive force. It's a force attracting bodies together. And it is a force that requires a minimum of 2 objects to feel the force. So in other words, a single object has the force of gravity, but to be able to measure that force of gravity, you have to have 2 bodies that are gravitationally interacting with each other. Now, the masses of the 2 bodies are the m1 and the m2 in the formula. So if, let's say, it is the force of gravity between you and the Earth, and your mass is one of the m's, and the mass of the Earth is the other m. So m1 and m2 are the masses of the 2 bodies. Now, if it were more than 2 bodies, let's say it's the force of gravity between the Earth and you, and then the moon added to the picture, then you would put in another m. One of the masses would be you, the other mass would be the Earth, and then a third mass would be the moon. So you can put in as many m's as necessary. Now, r is the distance between the 2 bodies, and an important clarification that needs to be made here is that the r is the distance from the center of one mass to the center of the other mass. It is not surface to surface. It is center to center. And the G is called the universal gravitational constant, and what that represents is just a constant of proportionality that allows us to make this an equal sign. In other words, it is what puts a number or a numerical value to this whole concept. Otherwise, it would be just a proportional thing. You would not be able to calculate a precise number that represents the force of gravity. Now, the universal gravitational constant has a value, and I wouldn't worry about memorizing the number or putting a full understanding into it. But what I want to point out is, notice the number has a 10 to the negative 11th power. Now, sometimes people get a little confused. The negative sign doesn't mean this is a negative number. You'd have to put the negative sign in front. What the negative exponent means is that it's a number that is greater than 0. It's a positive number, but it's less than 1. And with a very large negative value to the exponent, it means it's a very tiny, tiny number. So 6.67 times 10 to the minus 11 is 0.00000 all the way down to the 667. So it's a very, very tiny number. Now, the reason why I mention that is because it may be surprising to you to know that gravity is the weakest force in our universe. There are 4 fundamental forces of our universe. Gravity is one of them, and gravity is by far the weakest force in our universe. And it's surprising because obviously gravity can be very powerful, but of all the forces of nature, it is actually the weakest of the forces, and that's partly shown by the very, very small value to the capital G. So these are what the variables mean. Now let me show you why the formula is the way that it is. In other words, why is the R on the bottom? Why are the M's in the top? Let me show you some things that you probably already know, but let's at least sort of say them out loud so we can understand them. Now the thing is about gravity is its force depends on the masses of the bodies involved. If you have 2 objects that are of little mass, very small mass, then the force of gravity between them is also very small. An example is when 2 cars drive down the road in opposite directions, let's say one's in one lane and the other's in the oncoming lane, as the one car drives past the other car, there is a force of gravity between those 2 cars, but you won't feel that because the force is actually very, very small. The mass of a car, relatively speaking, is very, very small. So you don't feel the force of gravity from another car passing you and driving by you. However, if the masses are very, very large, then of course gravity is also very, very large. An example would be one of the masses, if that's the Earth, and the other mass, if that's the Moon. 2 large masses have a very powerful force of gravity, a force of attraction between them. So in science we say gravity's force scales directly with mass. When the mass is small, the force is small. When the mass is large, the gravitational force is also large. Now, the other thing we know about gravity is that it changes with distance. So if the 2 bodies don't change mass, in other words, it's the same bodies at all times, but all we're doing is changing their distance, what we know is the force of gravity changes with that changing distance. And you'll notice the arrow size is changing. The point of the arrow size changing is to show you how gravity's force changes with distance. When objects are close, the force of gravity is powerful. When those objects get further away, the force of gravity gets weaker. So gravity as a force decreases with the increasing distance. What that means is the force of gravity between the 2 bodies is getting lower the further apart they are. So when they get further apart, they feel a weaker force of gravity between them, and when they get closer together, that force becomes stronger. Now, having said all 3 of these things, that's what the formula is actually saying. Notice that the F and the M's are directly proportional. If the M's get big, the F has to get big. If the M's are small, then the F has to be small. That's what this is saying up here. So notice if M is small, force of gravity is small. If M is large, force of gravity is large. That's a direct proportionality. Now you'll notice in the bottom is an inverse proportionality. The force goes down as the distance goes up. And so that's why the R is in the bottom. So as R becomes bigger, they're further apart, the force of gravity gets weaker. This is an inverse proportionality. So when Isaac Newton puts this together, he's really just simply putting a formula together that describes what you already know, or at least what we sort of, in a very cursory way, know about gravity is how it behaves. He's just putting it into a formula so that we can now calculate it and be able to understand it in a bigger way. Now there's one last thing that we need to do. In other words, why is the r squared? We now know why it's in the bottom, because it's an inverse proportionality, but why is the r squared? Well, let me show you why. What I'm going to show you is a graph that is showing you the force of gravity as two objects are changing their distance. So in other words, if let's say you could take the moon and the earth and you could make the moon get further and further and further away, in other words, its distance would grow, well, what we just learned in the previous slide is that gravity becomes weaker as the distance grows. Now that's what this graph is showing you. In other words, as I start here on the left, that's a distance that's very, very small, meaning things are close, and that is a force of gravity that's very high. Notice that we start off right down here and way up here. So strong force because the distance is very small. Now, as the distance grows, the force of gravity is getting weaker. Notice that the force is less and less and less as we go further down. Now, if the r was not squared, then what would happen is this green line would cross this white line. And what that would mean is that gravity would eventually go to zero. You could have gravity just simply go away if you get far enough away from something. But what we know about gravity is that it doesn't behave that way. What we actually know about gravity is it behaves like this green line. Notice it's the same idea. As you get further and further away from one body versus another body, getting further away, the force of gravity is getting weaker with distance, but notice that it has a curve to it. And the reason why is because when we actually measure the strength of gravity and how it changes with distance, what we find is that it is actually following what we call an r squared relationship. Meaning, the further away you get, the weaker gravity becomes, but it becomes weaker by the square of the distance. So an example is, if the moon were twice as far away from the Earth as it is today, increasing the distance to be twice as far, 2 squared would be 4. The force of gravity between the Earth and the moon would be 1/4 as strong. So in other words, doubling the distance between the Earth and the moon reduces the force of gravity between them by 4 times. If I were to triple the distance, 3 squared is 9. So if the moon became 3 times further away, the force of gravity between them would be 9 times weaker, or 1/9. So gravity becomes weaker by the square of the increasing distance. Now, one thing that's related to that, and that's what this is showing here, it's becoming weaker very, very quickly. It drops off very fast. So it would be 4 times weaker, 9 times weaker, and then of course 16 times weaker, and then 25 times weaker as we're going bigger in distance. But what I want you to notice is this green line and the white line get closer and closer and closer, but they actually never touch. So what that means is that the force of gravity never goes away. In other words, you can never get far enough away from something to have its force of gravity become 0. You cannot escape the force of gravity of any object. The only way to do that would be to go to an infinite distance, but obviously you can't get infinitely far away from something in our universe. So what's interesting to know is the force of gravity never goes to 0. So right now, even though you're close to the Earth, you're feeling the force of gravity. If you were to leave the Earth and get further and further away, the force of gravity of the Earth would keep pulling on you. It would get weaker and weaker, but it would never go to 0. And the flip side of that is, that means every object in our universe is pulling on every other object in our universe. It's like a web of gravity between all objects. Now, you might be confused. You might say, well, wait a minute, what about things that are really massive, much more massive than the Earth? For instance, what if we were to compare the force of gravity of the Earth pulling on you and, let's say, the entire galaxy we call the Andromeda galaxy? Think of all the hundreds of billions of stars in this galaxy. Well, This is clearly much, much more mass than just the Earth is. But the Andromeda galaxy is very, very far away, and the Earth is actually very close. So the Earth has a greater influence on you because it's much closer to you than the Andromeda galaxy is. But don't kid yourself. The Andromeda galaxy is pulling on you, but with just a very minuscule amount of force. So what you can see is that gravity is a force of attraction, but it has a behavior that depends on the masses of the bodies and the distances between the bodies. But it's important for you to understand how that force changes with distance. It's an inverse squared relationship. In the next video, we're going to put all this together and finally get to the idea of what it means to orbit. And we have a couple more things to cover. I hope you'll join me.